There are two conductors. They are having same resistance at 0 degrees Celsius. So at 0 degrees Celsius, two, two resistance R1 is equal to R2. Let's consider it as R. Now we need to find the temperature coefficients of them when they are connected in series and parallel. So their individual temperature coefficient is given, that is alpha 1 and alpha 2. So first of all, we should know how this resistance is going to change with respect to temperature. So resistance at a temperature T equal to resistance at 0 degrees Celsius into 1 plus alpha into delta T. So this delta T is change in temperature. So initially, since it is a reference point is 0, so this should be uh, subtracted from 0 degrees Celsius. Fine. So we'll do for series. When two resistors are connected in series, the equivalent resistance is R1 plus R2. So at 0 degrees Celsius, what will happen to this R equivalent? It is R plus R, which is 2R. So let's use this particular equation and figure out the equivalent resistance at temperature T. R equivalent at T equal to R1T plus R2T. So this will be 2R because at 0 degrees Celsius the equivalent resistance is 2R. So 2R into 1 plus alpha equivalent into delta T equal to R into 1 plus alpha 1 delta T plus R into 1 plus alpha 2 delta T. So the R can be cancelled on both the side. And let's rearrange this. 2 plus 2 into alpha equivalent delta T, which is equal to 2 plus alpha 1 alpha 2 into delta T. So 2 will get cancelled and we'll get alpha equivalent equal to alpha 1 plus alpha 2 by 2. So this is for series. Now let's do the same thing for parallel. So in parallel, the equivalent resistance, we have to take the reciprocal and then add them. So at 0 degrees Celsius, this R equivalent is going to be 1 by R plus 1 by R, which is equal to 2 by R. So the R equivalent is going to be R by 2. Now let's write the same equation in parallel form. So it is going to be R by 2, 1 plus alpha equivalent into delta T, which is equal to 1 by R into 1 plus alpha 1 delta T plus 1 by R into 1 plus alpha 2 delta T. 1 plus alpha 2 delta T. So the R can be cancelled and we can simplify this one. So this will become 2 by 1 plus alpha equivalent delta T, which is equal to, let's take the LCM and do things. This will become 1 plus alpha 1 delta T into 1 plus alpha 2 delta T, and here we'll get 1 plus alpha 2 delta T plus 1 plus alpha 1 delta T. Now we'll cross multiply. So 2 into, I'm going to bring this term here and this term here. Also we'll multiply this. So 1 plus alpha 1, no, alpha 2 delta T plus alpha 1 delta T plus alpha 1 alpha 2 delta T square, which is equal to 1 plus alpha equivalent delta T. Here I can simplify the numerator. 2 into alpha 1 plus alpha 2 delta t. So again, let's simplify this one. This is 2 into 1 plus alpha 1 alpha 2 delta t, and we can just neglect this t square. It's not equal to 0, but we can just neglect it because it's very small compared with delta t. And similarly, we'll find here also. So the first term will come as it is 2 plus alpha 1 alpha 2 delta t plus 2 alpha equivalent delta t plus alpha equivalent alpha 1 alpha 2 delta t square. Again, we can neglect this one also. So we left with 2 into 1 plus alpha 1 alpha 2 delta t, which is equal to maybe I can expand this LHS. This is going to be 2 plus 2 into alpha 1 alpha 2 delta t, which is equal to 2 plus alpha 1 alpha 2 delta t plus 2 alpha equivalent delta t. So the 2 can be cancelled and we can subtract this alpha 1 alpha 2 delta t. So alpha 1 plus alpha 2 into delta t, which is equal to 2 into alpha equivalent delta t. The delta t will get cancelled and the alpha equivalent will become alpha 1 plus alpha 2 by 2. So this is for parallel. So if you look at in series also we got the same expression. So irrespective of parallel or series, it is going to remain same.